Hey guys, my name is Pedram and I'm a professional practice assistant professor in finance. I'm also a CFA charter holder. This is another episode of my crash course in machine learning concepts, simply explained. Alright, in previous part we talked about logistic regression model and we compared it to the linear probability model. We discussed that logistic regression is a supervised learning algorithm and it's a kind of a parametric model. It means that we are imposing a functional form to the model. We use logistic regression as a classifier. That means that at the end of the day, the logistic regression is going to give us this decision boundary. And based on that, we are able to categorize the observations in the test set. Let's say to the left of this boundary, everything is going to be 0. To the right of this boundary, the model is going to predict everything to be 1. In this part, we're going to see how the model is able to come up with this classifier. In other terms, what is the estimation techniques in order to estimate the parameter of the model. So part 18, logistic regression, the objective function. And we're going to use MLE, maximum likelihood estimation, to estimate the parameter of the model. In logistic regression, instead of minimizing the average loss, this is what we do in regression analysis in general, right? Here we are maximizing the likelihood function, the likelihood of observing the training data according to our model. This is called maximum likelihood estimation. So let's see what is MLE and how it's doing the job of estimating the parameters of the model in action. So what is the likelihood function? The likelihood function basically describes the joint probability of the observed data as a function of the parameters of the model. In simple word, it basically says that what's the probability that the data is coming from this specific model that you're investigating, right? Now let's look at some examples and see how the MLE is adjusting the parameters to maximize the likelihood function. Okay, so here imagine we have two classes, and this is a very simple example. So let me use green, and we are going to say that, okay, so let's say we have two classes, red and blue, and we have only 4 observations, right? So this is going to be our y variable, this is going to be our x variable. X is one, for example, a feature, and y can be any categorical variable, right? Pass or fail, blue or red, and a loan application has been approved or denied, buy or sell, whatever you can think of, right? So let's say we have very simple 4 observations in this data set. Two of them are actually red and 2 of them are actually blue. And on the y-axis, we have the probability of blue, right? So this is and blue can be anything, right? The probability of blue and goes from 0 to 1, right? And now let's imagine that we know that these 2 observations, let's call them 1, 2, 3, 4, or we can rename them as A, B, C, D. So let's call them A, B, C, D. So let's say this point A, B, C, and D. We know that observation A, in reality, it's red, right? But what's the prediction of the model? So the prediction of the model is this number, this probability. So this is what the model is predicting. So let's say the model is predicting 0.2. So the probability that this observation is blue is only 20%, right? And the same story for point B. So what's the probability that point B, the model is predicting, what's the probability that's blue? So let's say it is 75%, right? And what's the probability that the model is predicting C is blue? So the probability is going to be, let's say it is 80%. And finally, what's the probability that D is blue? It is going to be, let's say 90%, right? Then, so these are the outcomes of the model. Then we need to come up with a threshold to classify them, right? So let's say that the threshold is 50%, right around here. So this is our threshold, 50%. So anything above the 50%, the model is going to call it blue. Anything below the 50%, the model is going to call it red, right? So what are the predictions? At the end of the day, the model is going to predict point D to be blue, point C to be blue, and point B, the model is going to misclassify it as blue, right? Because the threshold is 50% and the probability is 70% here. So it's going to be classified as blue. What about point A? The model is going to correctly predict it to be red, right? Now, if I ask you, for example, what is the we know that these are the real data, right? The real data, D is blue, C is blue, B is red, and A is red, right? Now, if I ask you, what is the joint probability of observing the data based on this model, or simply put, what's the probability that the data is coming from this model? What's your answer? So we have to multiply the probability of these points happening, right? So what's the probability that D is blue? So the model predicts, so we call this function likelihood function, right? So what's the probability that D is blue? We said it's 90%. What's the probability that C is blue? We said it's 80%. Oops, sorry. We said that it's 80%, right? Now, pay attention here. What's the probability that B is red? We know that the probability that B is blue is 75%. So what's the probability that B is red? It's 1 minus 75%, right? So it's 1 minus 0.75. And the same story for what's the probability that A is red? So we know that the probability that A is blue is 20%. So the probability that A is actually red is going to be 1 minus 20%, right? So this is a likelihood function. And if you go ahead and do the math, this is the number you get, right? So 14.4% is going to be the joint probability of the observed data based on the parameter of the model. So what do we mean based on the parameters of the model? So look at this S-curve. So this is our S-curve, right? So this S-curve has some parameters, right? So this is logistic regression, and the parameters are, so here because we have only one feature, it's going to be W1 X plus B. So these W1 and B are the parameters of the model. And with some specification for some values of W and B, this is going to be the shape of the S-curve. Now, let me go ahead and change the parameter of the model. So this is exactly what the maximum likelihood is doing behind the scene. It's going to change the parameter of the model to come up with another likelihood function, right? So changing the parameter, what does it mean here? It means that we are shifting the S-curve left or right, up or down, and etc., right? We are shifting it inward and outward. And then we're going to recalculate the likelihood function. So, and it's going to do this process again and again to maximize that likelihood function, right? So let's look at another S-curve with different W1 and B. So imagine this S-curve has another, let me call it W prime 1, X plus B prime, right? So this is another representation of the S-curve, right? Now let's recalculate these likelihood functions, right? Again, this likelihood function. Again, we are talking about point A, B. These are exactly the same point, right? C and D in reality are blue. A and B in reality are red, right? So here again, the probability of blue is 0. Probability of blue is 100%. Now let's go ahead and calculate and see if the model is correctly predicting or is doing misclassification or not, right? Again, to be consistent, the threshold should be 50%. So let's say this is our threshold, 50%. And now look at the probabilities. Let's start with point D. So for D, what's the probability? Let's say here, this is point D. What's the probability that the point D is basically blue? Let's say this is 85%, right? And the model correctly predicted to be blue because 85% is greater than 50%. For point C, what's the probability that is blue? Let's say it is 60%. And the model correctly predicted point C to be blue because 60% is greater than 50%. And then let's go to point B. So what's the probability that point B, look at that, what's the probability that point B, that observation B is blue? So this is what the model is going to predict. The model is going to predict that, let's say, 40%. And as you can see, this is correctly classified as red because the threshold is less than 50%. Same story for A. Let's say, what is the probability that point A is blue, the probability is only, let's say, 20%. So the model is saying that, okay, there's only 20% chance that this point A is blue. This is a good number, right? Because we know that it's well below 50%, and the model is going to correctly specify it as class red. So in this example, there is no misclassification, right? So everything is correctly classified. And now let's calculate the likelihood function. We know that the likelihood function should be higher, right? So let's see that. So this is the probability of point D, right? This is probability that the model predicts for point C. This is the model that this is the probability that model correctly predict for point B. You know that it's 60%, right? It is 60% red, and this is the probability that model predicts for point A to be red. So it's again correctly predicted 80%. Then if you multiply these numbers to calculate the joint probabilities, you will get 0.244. And now if you compare these two numbers, 0.144 and 0.244, and as you can see, the likelihood function is increasing. So the likelihood function is increasing based on different values for W1 and B, right? So this is how actually the MLE is doing the job behind the scene, right? In order to maximize the likelihood function by changing the parameters of the model. And this way, we are going to maximize the probability that the data is coming from this model with this specific parameters. All right. Now, let's formalize what we discussed in the previous slides using machine learning notation, right? So this is the S-curve function, and as you can see, for different values of, let's say B, this is the bias term, and this is our W1. For different values of B and W1, we get different shape of S shape, right? And we are trying to maximize the likelihood function. So this is our S-curve, right? This is, we know that it's, we're using the sigmoid transformation and apply it to our linear model, and this is what we get, right? And this is a likelihood function. The likelihood function is a function of W's and B. We know that in higher dimension we have multiple W's and one B. This is our multiplier operator, and this is the probability of class 1 happening. In the previous example it was blue. This is the probability of class 0 happening. In the previous example it was class red, right? So basically we are multiplying these probabilities to get the joint probability of observing the data. All right. Now, let's look at the objective function for the logistic regression. So in logistic regression, as we discussed earlier, and now we are formulating it more formally, we're doing this. We're maximizing the likelihood function, right? So this is our likelihood function that we just covered, and we're maximizing this function. So the solution to this problem, in practice, it is more convenient to maximize the log likelihood instead of likelihood itself. Because as you can see, if I take log from both ends, I'm maximizing the log likelihood here. And because log is a monotone transformation, it's strictly increasing, it really doesn't matter if I'm maximizing log or the likelihood itself, right? But the right-hand side is going to become a lot more convenient to work with, because if I take log from the right-hand side, this multiplier operator is going to become a summation operator, right? So now we are going to add these probabilities to each other. And in order to find a solution, it is a lot more convenient and easier for computer to work through iteration and find the optimal value for W star and B star. So this log likelihood maximization is going to give us the W stars and B star. And as you can see, unfortunately, there is no closed form solution to this optimization problem. And we have to use our gradient descent solvers, right? Gradient descent and its family, the ones that we already discussed in the previous parts. All right, so we are now ready to make predictions because at the end of the day, we have W stars and B star using the MLE. And now we can simply put it in our function, which is the S-curve. So we know that the F of W and B. So we plug these numbers here into parameters, and then we add some test set here. And the model is going to give us some probabilities, let's say 80%, let's say 60%, let's say 15%. And then, depending on how we define a threshold, we come up with the classifier. If the threshold is 50%, these two classes are going to be 1, this class is going to be 0. If the threshold is 65%, then these two classes are going to be class 0, this is going to be class 1, right? All right, so let me erase this part. Depending on how we define the probability threshold, this is what we just discussed, right? We can classify the observations in practice, right? In practice, the choice of the threshold could be different depending on the problem. So let me give you a quick example of why do we care about this threshold. For example, you're doing some COVID tests, right? So you're looking at the COVID test results, and you want to be conservative in terms of to avoid too many false negatives, right? Because you don't want to send people out in the society with false negatives, right? So in that case, we're going to discuss it later on that in order to avoid too many false negatives, we have to reduce the threshold. So instead of, let's say, 50%, let's work with 30%, 20%, because you want to avoid getting too many false negatives. You want to be more conservative. Another example from the other end is, for example, you're thinking of a spam detection problem, right? And you know, you want to make sure that the emails that you get are not you avoid too many false positives, right? So you want to make sure that if the email is really, let's say more than 70%, 80%, or even 90%, you're confident that it is a spam, then let's label it spam, right? You want to be conservative. You want to avoid too many false positives, right? You don't want to see that, for example, the email that you get from your university professor go to your junk box, right? So for that reason, in that example, you're going to increase the threshold to avoid too many false positives. So in a nutshell, this choice of threshold depends on the research question, but by default, we have, you know, in Python in other programming languages, by default, the threshold is set to be 50%, right? So always think about this example of COVID versus spam detection. So if you want to avoid too many false positives, you increase the threshold. If you want to avoid too many false negatives, you decrease the threshold. All right. Let's conclude this episode by looking at the logistic regression outputs for credit card default example that we investigated in the previous episode. If you remember, we were interested in to see if someone is going to default or not on their credit card based on their credit card balance and their income, monthly income, right? This is monthly balance and monthly income. And so here we have logistic regression. It means that this is our functional form that you're imposing to the model. We're using sigmoid transformation, and this is what we get at the end of the day. So this is going to be the model, the classifier, f of w and b, given the features, right? At the end of the day, this classifier is going to look like, in 2 dimensions, it's going to look like this. So it's a line that is going to call anything on the right-hand side 1, anything on the left-hand side 0, right? So we're going to use MLE and gradient descent to come up with the optimal values for W stars and B stars. So we have W star 1, W star 2, and B star. And with that, we will come up with our optimal value for the classifier, right? So what is the optimal classifier? Based on that, the model is going to make some predictions for every single observation, right? So let's say one is 80%, the other one is 85%, the other one is 10%. Then we come up with a threshold, and based on that threshold, the model is going to enable us to classify things, right? Call them default versus no default, right? So, and this is how the visualization is going to look like. If you're curious to look at the Python code, please make sure that you tune into my machine learning applications in finance course, which is available on the YouTube channel, and you can access the codes and slides and everything over my GitHub account. Okay, so on the vertical axis, we have income. Horizontal axis, we have balance. And as you can see, the features are scaled, or already scaled. So the feature scaling is not that important for logistic regression itself, even though it's going to speed up the process, but it doesn't make a huge difference. However, if you wanted to combine logistic regression with one of the penalized regression models that we already talked about, like Ridge, Lasso, and ElasticNet, then you must scale the features, because remember, in those penalized regression models, we were calculating the norms. We were using L1 norms, L2 norms. We were calculating the distances. And whenever in machine learning in general, you're calculating distances of observations from each other, it is better to scale the features, right? So, and if you're curious how we combine the logistic regression with the penalized regression model, it's very simple. The idea is that, for example, you are maximizing the likelihood function. Now, you just need to add its constraint. If the constraint is, for example, the summation of, let's see, if the summation of WJs is less than a number, let's call it alpha. So here we're using L1 norm, right? So you're combining the lasso with logistic regression. If you use L2 norm, so for example, if you add this constraint, summation of WJ squared less than or equal to, again, some number, let's call it gamma, then you're using L2 norm and you're combining the ridge regression with logistic regression, right? And if you combine all these things, you get a combination of elastic net with logistic regression, right? So if you're doing it that way, you want to penalize the coefficients, the features themselves, then you should scale the features. But if you're using logistic regression and the scales and the features are not that different in terms of scale, it doesn't matter if you don't scale the features. However, it doesn't hurt the model eventually if you scale the features. So let's go ahead and do that. So this is what we do here, right? And at the end of the day, based on this classifier, that we have a functional form for that, we can say the model is going to predict anything on the left-hand side. The y hat is equal to 0. So these are the predictions. So the background color are the predictions. And here y hat is equal to 1. It means that the background color, red, the model predicts always red, right? Let's say in this case default. And the dot themselves are observations. So for example, this green dot here, this is one, so this individual no default. So y itself is equal to no default. And for this individual, the red one here, y is equal to default. So this individual in the real data actually defaulted, right? So as we talked about it briefly last class, the red dots on the red background, these are good predictions, right? The green dots over the green background, these are also good predictions. So what are the misclassifications? These are, so for example, a red dot on a green background is misclassification. This is a misclassification, right? Now let's give them some names, right? So let's give them some names, and basically for that we're going to use something called confusion matrix, right? So at the end of the day, you made some predictions and you want to see what's the performance of the model, if the model is performing good or not, right? For that, we need to report these classifications in terms of if they're good numbers or bad numbers, right? So let's say here is actual versus predictions, right? So in actual, if you have two classes, we can have 0, no default, 1, default. For predictions, we can have no default and 1 default, right? So if in reality we are dealing with no default and the model also predicted no default, so these are true negatives. These are good numbers, right? So in reality, these observations didn't default and the model predicted no default. So these are good observations. And if in reality if in reality the observations were actually default and the model predicted default, these are also good numbers, right? So true negatives, true positive. So how can I see it on the graph? So this is an example of true negative, right? So this is what the model is correctly predicting, no default. This is an example of true positive. The model is correctly predicting it to be true positive. So the goal is to maximize these true positive and true negative and minimize the false predictions. What are the false predictions? Let me use red. These are false predictions, right? In reality, this observation, this individual did not default, but the model predicted that it default. So this is a bad number. The same story, we call it false positive. The same story for here. In reality, they did default, but the model predicted that no default. So these are false negatives, right? How can we see them here? So let's look at these ones. These are false positive, right? The model predicted them to be 1, but they were actually 0. They were actually green, but the model predicted them to be red, right? So this is false positive, and this here, let's say this one, is our false negative, right? So the model the model predicted to be negative, but in reality it was positive. It was red. Okay. So this is false positive, false negative, true positive, true negative. So in short, these are good numbers. True negative and true positive are good numbers. False positive and false negative are bad numbers. And based on how we combine these numbers with each other and report the statistic, we come up with different classification statistics in general, measures in general. So for example, here, if you simply say that I want to look at the accuracy of the model, right? Overall, how many observations were correctly predicted? How do you do that? So this is, we're going to define these things in more details in the next video, but let's go over the accuracy quickly. So this is how we define the accuracy, right? So what are the good numbers? True positive plus true negative, and divided by entire observations. So what are these entire observations? True negative plus true positive plus false negative and false positive, right? So basically the good numbers, 20 plus 1933, divided by the entire observation. So if you add them all, you will get 2000, right? So it will be close to 97%, right? So it seems that the accuracy of the model is 97%. If I look at this statistic, right? So you may get excited and say that, okay, 97% is awesome. So this model is doing a great job. However, we should be very careful. As we can see here, this data set is very imbalanced. So out of 2000 observations, only 3% of them are no default. So maybe looking at the accuracy as a performance statistics is a little misleading. So what other things we can look off? So we can look at precision, recall, F1 score, MCMC, and etc. So these are all the classification performance metrics that we're going to investigate in the next lecture. Until then, take care and see you in the next one.